physical addresses on the one side. Physical addresses are those addresses physically inside the RAM chips of your computer. So if you buy a computer that's got 4 gigabytes of RAM, your computer will have memory addresses, physical addresses, up to 4 gigabytes. You can go and look at the big hexadecimal values of that, but that's the highest address that you can get in the RAM of the computer. You cannot go higher than that. The logical addresses is something totally different, potentially mapped somewhere else. Inside your CPU, you have a component called the memory management unit. Not separate from the CPU, it's in the CPU itself. Now, what is the role of the memory management unit? Now, depending on the, let's call it the version or how new this CPU is, the more complicated this memory management unit. The original, very simplistic memory management unit has a specific role, but effectively it translates logical addresses into physical addresses. So it takes, CPU says, I want to access memory address 840000. The NMU does that and translates that into the physical address of where it actually is stored in. So hopefully you can see that there can be a disconnect between the logical and the physical. They can be two different addresses. And the NMU helps us with that translation. So there's many different ways in which this translation can work. They mentioned the NMU, for instance, on the original MS-DOS, basically used 4 what they call relocation registers. Remember this right? I think it was the code segment, data segment, enhanced segment, I think. Oh, I can't remember. But there was a few of these registers that they used to relocate what they call the start addresses of your physical address. So user program deals with the logical addresses. So from a user's perspective, the stuff that I showed you there in the debugger, that's logical addresses. The actual physical addresses is not known by now. I don't know where it is physically in my computer. Alright, so the slide on the second world version, this had an incorrect title. They actually had a relocation register or something there, but it didn't fit with the words. But this diagram on the right side actually explains how the NMU, together with a very simplistic relocation register, actually works. So the CPU, for instance, in this example, will have a logical address of 346. When it says, I want to access whatever, either an instruction or a piece of data or a whatever, at memory 346. And then the NMU looks at the value that's in the relocation register, adds those two together to get the actual physical address. And this happens even on modern CPUs, but in a little bit more complicated scale, which we'll demonstrate later. So there's all of this relocation happening all the time inside the computer. Another thing, which is actually what the wording on the slide is all about, nothing to do with the diagram. So this diagram goes together with this thing, right? The dynamic loading portion, it does explain that when you develop applications, you can develop an application to use a principle what they call dynamic loading. And what dynamic loading basically means is that when you've got procedures or functions or routines, that we don't always have to load all of those routines from the exe into the memory. That's the fancy thing about dynamic loading. Dynamic loading basically means you've got your main function loaded into the memory, and then as we require certain routines, only then do we load that into the memory of the computer. The routines are kept on disk in what they call a relocatable load format, so that basically when we load them into the memory, we can relocate them anywhere in the memory, but we can find them using our relocation registers. So we basically use the relocation registers to always allow us to know the offset of where they will physically will be. This is useful for what purposes? When large amounts of code are needed to handle infrequently occurring cases. I mean, if you write a program, there's some error handling and those kind of things that you might be writing in your code. Normally, probably at 99% of your process runtime, that code is never accessed. So, but it must be there in cases of errors occur. So only when that errors do occur, do we then load it into your computer, and that is necessary or used. Basically, for dynamic loading, there's no support from the operating system required. It's implemented through the program design. Typically, the compiler helps with this. And the OS may provide certain VLL libraries to help us with the dynamic loading. Now, expanding on this principle of dynamic loading is this principle of dynamic linking. Now, this you had, or you did in your first, I don't know if you can remember this. Prof Filter and, sorry? Mr. Greaves, yeah, he basically, they took you through this process where you could compile a program, and you had two ways in which you could compile it. So remember, when you wrote a C++ application, you didn't have to write all the code to do the output to the screen and many of those things. That code exists in libraries. Now there's two ways in which these library code can be added to your program. So one is what they call static linking. Now what that basically means is when you compile your code, it fetches that library code and puts it inside the exe file. And that makes the exe file typically grow quite big. I mean, let me show you. I still have that open. Let me see if I've got it. Yeah. So what you see here is this is a very simplistic Fibonacci application that's now compiled. And this thing is 141 kilobytes. That's 141,000 bytes inside. But the amount of code is maybe 20 lines of code. So how is it possible that 20 lines of code is that big? It's because it takes all of these necessary libraries and adds it into the actual exe. That's called static linking. Dynamic linking is if you've got library code, instead of adding it into the exe file, what happens is in the program, inside the exe, we have what they call a stub. So there's a little pointer actually that says, hey, when you get to this point, go to another file, open that file, get the code, and load that thing into the memory of the computer. So static linking, the nice thing about it, you can basically wrap your application in one exe file, you can give it to someone and it will work on that specific version. Dynamic linking allows us to, for instance, have our shipped version of our application be a lot smaller. As long as the libraries are available on the computer, the actual program is a lot smaller. And it helps us to, for instance, update portions of our code without having to recompile the actual application. If we, for instance, get a new version of the library, that version of the library can get updated, and because it's dynamically linked, we immediately get the new version of the code there. Now this should already show you something. Remember we're talking about main memory and how we work with things. So in this case, with dynamic linking, not everything has to be in memory when we start our process. Sometimes, as we use these libraries, only then do they get loaded into your computer. One big advantage of using this, obviously, is when we work with our program. So let me rather ask this. Maybe you haven't seen this, but the second Tuesday of every month, something special happens with Microsoft operating systems. Who knows what? Second Tuesday of every month, your Microsoft operating systems, they go through a security patch updates. It's called the Patch Tuesdays. So normally at that point, the operating system goes to the internet, says, hey Microsoft, actually they do it every day, but normally on Tuesday, that's when they release these new security patches. When a new security patch comes out, it means that something